Dear students, in the previous lecture, I have told you to solve this problem which was asked in March 2014 annual examination. So in this problem, it is given that there are 4 charges Q, 2Q, 3Q, 4Q kept at the 4 corners of a square of side 0.1 meter. If the resultant electric field at the center of the square is 5.1 into 10 to the power of 3 Newton per coulomb, you are asked to find this charge Q. In the problem which you solved before this one, 4 charges were given and you found the field at the center. In this particular problem, field at the center of the square is given. You are asked to find this charge. The basic procedure in solving this problem is the same. So first you represent the directions of these electric fields. Due to this positive charge at this point, electric field is along AO in this direction. Similarly, due to this charge at QQ at the point O, the electric field is along BO. Similarly, due to the charge at C, electric field is along CO. Due to the charge at D, electric field is along DO. The magnitude of electric field at O due to the charge at A, this one. Due to this charge at this point, magnitude of electric field is given by this equation. Electric field at a point due to a point charge. 1 by 4 pi epsilon Q divided by R square. So this is K, charge is Q, and the distance is AO. So this is the field at O due to the charge at A, and its direction is along AO. Similarly, the field at O due to the charge at B, it is given by this equation. So this OA is equal to OB is equal to OC is equal to OD. Distances are same, but this charge at B being a double that of A, electric field will become double. So it is 2 times this equation, 2 EOA along BO. Similarly, electric field at O due to the charge at C, it is 3 times along CO, and at D it is 4 times along DO. Now here these 2 fields EOC, EOA, these 2 being in opposite directions, they resultant here EOC minus EOA. Because this EOC, this is 3 times that of EOA, therefore the resultant of these 2 is 2 EOA along CO. In the same way, the resultant of EOB and EOD, here EOD is stronger than EOB, therefore the resultant is also 2 EOA along DO. So here the magnitudes of E1 and E2, they are equal. Magnitudes of E1 and E2 are equal, but their directions are different. So to find the resultant of this E1 and E2, according to parallel law, you will get this equation. In this equation, since E1 is equal to E2 and this theta cos 90 being 0, this equation will become root 2 times E1. So this E1 is 2 times EOA. Now you substitute for this EOA and you find the value of Q, it comes to be 1 nanocoulomb. So this is the answer which you are supposed to get. I hope all of you have done this problem correctly. That means you understood the procedure to solve these type of problems. Sometimes a little bit more complicated problems can also be given in the examination like this. We shall take another problem now. Here is a problem. ABCD is a square of side 0.2 meter. Charges of 2 nanocoulomb, 4 nanocoulomb and 6 nanocoulomb are placed at the corners AB and C respectively. Calculate the electric field at D. So this is a little bit different problem. So in case if you could not get this answer, just you go through this solution and you find out where you committed mistake. So in this problem there is a square ABCD. So A, B, C, D. The square is of side 0.2 meter and the charges of 2 nanocoulomb, 4 nanocoulomb, 6 nanocoulomb are placed at corners A, B and C respectively. A, B and C, these three charges are there. Now the question is, calculate the resultant electric field at D here. At this point you are asked to find the resultant electric field. So first you represent the directions of electric field at D due to the individual charges. Due to the charge at A, at this point electric field is in this direction. So this is EDA, electric field at D due to the charge at A. Similarly, due to the charge at B, so this is the direction of this electric field. So this is EDB. So this is a positive charge. At this point electric field is directed away. Next, due to the charge at C, the electric field is along CD. So this is EDC. So we represented the three electric fields. So to find the resultant of these three vectors, first you have to reduce the vectors into 2. For that, what you do? You split this EDB into rectangular components. So this being a square, this angle becomes equal to 45 degree. So you split this component this side, which is E, when this is 45, this is also 45. So this becomes EDB cos 45. So here it becomes EDB sin 45. So this has been split into two components like this. Now this EDA, EDB cos 45 both are in the same direction. You find their resultant E1. Next, these two are in the same direction. You add these two and you find the field E2. Next, E1 and E2 are perpendicular to each other, so you find the resultant electric field at the point D. So this is the procedure to find out the field at D. Now shall try it. See, in this triangle, in this square, this BD, diagonal. This BD, it is root 2 times the side. That means root 2 into 0.2 meter. So first let us find electric intensity at D due to charge at A. EDA 1 by 4 pi epsilon naught QA divided by AD square. So 9 into 10 to the power of 9, 2 into 10 to the power of minus 9 divided by 0.2 whole square. So these terms can be cancelled. So this is 18 divided by 4 into 10 to the power of minus 2. So it is 2.5. 2.5 10 to the power of 2 Newton per Coulomb along AD. So this field magnitude is this much and the direction is along AD. Similarly, this EDB 9 into 10 to the power of 9. This charge is 4 nanocoulomb, 4 into 10 to the power of minus 9. And what about this distance? Root 2 into 0.2 whole square. So again this term can be cancelled. So this is 36. 2 into 4. 2 into 4 into 10 to the power of minus 2. So this becomes 4.5 into 10 to the power of 2 Newton per Coulomb along BD in this direction. Next you find EDC, this one. 9 into 10 to the power of 9, 6 into 10 to the power of minus 9 divided by 0.2 whole square. So this is 9 into 6 into 10 to the power of minus 2 divided 10 to the power of plus 2 divided by 4. That means so it is 13.5 in 10 to the power of 2 Newton per Coulomb along CUD. So you check those numerical values. So this is 4.5. And this is root 2.2 whole square. So this is 2, 4, 10 to the power of minus 2, 36. 18 by 4, 18 by 4 means 4.5. Okay. So this is 4.5 into 3, 13.5 into the power of 2 Newton per Coulomb along C. So these are the three fields now. On resolving EDB into rectangular components, on resolving EDB into rectangular components, net electric field along AD E1, it is equal to EDA plus EDB cos 45. So this EDA it is 4.5 10 to the power of 2. 4.5 10 to the power of 2 plus this one 4.5 10 to the power of 2 1 by root 2. So you simplify this one. One plus 1 by root 2. You will get 1.7 because this is 0.707. That means 0.71 or 1.71 into 4.5. So you find this value. Similarly, net electric field along this side CD E2. This E2 is equal to EDC plus EDB sin 45. So this EDC, it is 13.5 in 10 to the power of plus 2, and this is 4.5 in 10 to the power of plus 2 1 by root 2. So if I take this 10 to the power of 2 common, 13.5 plus 4.5 by root 2 10 to the power of 2, you find this value. So this will be along CD. Therefore, resultant electric field at D, ED, it is equal to root of E1 square plus E2 square plus 2E1 E2 cos 90, because this angle becomes 0. So you calculate this E1 using your calculator, E2, you take those two values and you find ED. So when you do this calculation, you will get around 1.8 4 in 10 to the power of 3 Newton per Coulomb, and its direction will be 24.7 degree. With the CD. So this becomes the resultant ED, and this becomes alpha. So alpha is this is the magnitude and this is the direction. 24.7 degree with CD. So this is a little bit lengthy problem, just to make you understand how to resolve and find the resultant electric field at a given point. I took this example. So you finish up this calculation, this one here, substitute those values here, and you check whether you get this answer or not. I'll take another simple problem. Two charges 10 microcoulomb and 20 microcoulomb are placed at the corners of hypotenuse BC of a right angle triangle ABC. Sides AB is equal to 3 cm and AC 4 cm. Calculate the resultant electric field at the corner A. According to the statement given here, if I draw a diagram, it will be like this. Here there is right angle triangle. A, B, C. AB is given as 3 meter. This AC is given as 4 meter. And two charges, 10 microcoulomb and 20 microcoulomb, are placed at the corners of hypotenuse BC. So, this 10 microcoulomb is at B, this 20 microcoulomb is at C. Now the question is, calculate the resultant electric field at the corner A. See, this is a right angle triangle like this. At the hypotenuse BC there are two charges. This length is given, this length is given. You are asked to find the field at A. So this is the problem. Find the field at A. So as per the standard procedure, first you represent the direction of electric field at A due to individual charges. Due to this charge at B, the field at A is in this direction. So this is EAB. Similarly, due to the 20 microcoulomb charge at A, the field is in this direction. So this is EAC. This is a positive charge, field at a given point is directed away. This is another positive charge, field is directed away. So you calculate the magnitudes of these two fields, and by applying parallelogram law you find the resultant. It is very simple one. In the board examination, these type of simple problems will be asked in the examination for 3 marks in part D. So first, electric intensity at A due to charge at B, EAB 1 by 4 pi epsilon naught QB divided by AB whole square. So this is 9 into 10 to the power of 9, 10 into 10 to the power of minus 6 divided by 3 whole square. So these terms will cancel. So this will become 10 to the power of 4 Newton per coulomb along BA in this direction. Similarly, EAC, electric field at A due to the charge at C. So 9 into 10 to the power of 9, and this is 20 into 10 to the power of minus 6 divided by 4 square. So this will be 5 by 4, that is 9 into 1.25 in 10 to the power of 3. So this is 32.5. Eleven 11.25 10 to the power of 3. That means 1.125 10 to the power of 4 Newton per coulomb along CA. Therefore, resultant electric field at A is given by EAB square EAC square, and the last term becomes 0 because this angle is 90 degree. Now you do this calculation, this 10 to the power of 4, it can be taken out. So 1 square plus 1.125 whole square. If you find this value, you will get 1.5 in 10 to the power of 4 Newton per Coulomb. So this is the resultant field EA. Now if I take this as alpha, this alpha comes to be, this alpha is EAC. EAC divided by EAB. So from this, if you calculate this angle, it comes to be 48.4 degree with BA. So this is the solution for this problem. You look at the next one. Two charges, 5 microcoulomb minus 5 microcoulomb, are placed at points A and B. So this is 5 microcoulomb, this is minus 5 microcoulomb, they are placed at A and B. So this is A and this is B, which are separated by a distance of 0.06 meter. This one. Find the electric field at a point P on the perpendicular bisector of AB at a distance of 0.04 meter from this middle point. So this is the middle point of A and B. So perpendicular bisector. So this is the perpendicular bisector. On this perpendicular bisector at 0.04 meter, you are asked to find the field. So there are two equal and opposite charges separated by this much of distance. You are asked to find electric field on the perpendicular bisector at a distance of 0.04 meter. See, actually you tend to use the expression for electric field at a point on the equatorial line of electric dipole. That formula should not be applied here, because as you learned, dipole means two equal and opposite charges must be separated by a small distance. Small distance in the sense, this distance should be of the order of nanometer or at the maximum micrometer. So here this is not in terms of nanometer or micrometer, so therefore this system do not form a dipole. That is why you should not use the formula for electric field on the equatorial line of a dipole. So instead of that, you have to follow the conventional procedure. That is, by applying principle of superposition, you find the electric field at P due to the charge at A. So this electric field is in this direction. This is EP A. This is a positive charge. At this point, you find the magnitude of electric field, and this is the direction. And also you find the electric field at P due to the negative charge here. So this is EPB. Now this is a triangle, this is a triangle. So this angle here, it becomes equal to this angle here. Therefore this angle will become equal to twice this angle. Now this distance is 0.03 meter, because it is 0.06, that means this is 0.03 AO, this is 0.04, Therefore, this distance AP will become 0.05 meter because it forms a Pythagorean triplet. So AP, that is equal to BP, which is equal to 0.05 meter. Now you find this EPA, you find EPB, and later you find out the resultant field by knowing this angle. Electric field at P due to the charge at A, EPA, so this is 9 into 10 to the power of 9, 5 into 10 to the power of minus 6 divided by 0.05 whole square. So this will be 9 into 5, 10 to the power of 3 divided by 25 into 10 to the power of 4. So it cancels 5 times. So you will get 1.8 into 10 to the power of 7 Newton per Coulomb along AP. So this is 1 by 4 pi epsilon naught, this is Q, and this distance is AP. Because this angle is 90 degree, 0.03, 0.04 means it becomes 0.05. So it will be 9 by 5. 9 by 5 means 1.8 into 10 to the power of 7 Newton per Coulomb. Similarly, EPB, this is also 1.8 into 10 to the power of 7 Newton per Coulomb along PB, this side. See, these two fields are equal. So you resolve these two fields into perpendicular components. So this component and this components will cancel. So the resultant field will be in this direction. On resolving EPA, electric field at P due to the charge at A. On resolving EPA and EPB into rectangular components, resultant electric field at P, it is equal to root of EPA square EPB square plus 2 EPA EPB cos 120 degree, not 120, cos 2 theta. It is not an equilateral triangle. So it is not an equilateral triangle. Sorry, cos theta, not 2 theta. It is not an equilateral triangle. So if this angle is theta, then this component is EPA cos theta, this component is EPB cos theta. Oh, I use this formula, no? So it is you should do it like this. become 2 EPA cos theta. Because this component and this component cancel, the component of EPA this side is EPA cos theta and the component of EPB this side is EPB cos theta. Since EPA and EPB equal, these two being equal, it becomes 2 EPA cos theta. So this is 2 into 1.8 into 10 to the power of 7. 2 into 1.8 into the power of 7. What is this cos theta? Here cos theta is adjacent side by opponent, so it is 0.03 divided by 0.05. So you do this calculation, thereby you will get this field at P. Even without resolving them into components like this, without resolving them into components, you can take this equation as written earlier, root of EPA square, EPB square plus 2 EPA, EPB cos 2 theta, this angle. So you can do like that also. You will get the same answer. It comes to nearly 2.16 Newton per coulomb. So you can do it like this. Instead of following this procedure, straight away you can take it as EP is equal to parallelogram law of factor addition. So here this EPA square plus EPB square plus 2 times EPA EPB cos 2 theta. Even by taking this formula also you can calculate this one, you will get the same answer. So when you resolve into rectangular components, you get this equation. Without resolving into rectangular components, straight away you can use this parallelogram law of factor addition and you can get the answer like this. To look at another problem, an electric dipole of moment (2 into 10 to the power of -8 coulomb meter) is placed in electric field 5 into 10 to the power of -5 Newton per coulomb, with its axis making an angle of 60 degrees perpendicular to the field. So here this is the electric field and this is the dipole. And here this angle, it is given as 60 degrees. Now the question is, what is the torque acting on the dipole? So this dipole moment is given, electric field is given, this angle is given. From this you are asked to find the torque acting on the dipole. What is the basic formula for torque acting on a dipole? Tau is equal to vector P cross E. So if I take the magnitude, so it is P sin theta. What is this theta? In this derivation, I told you that theta is the angle between P and E. So this is the direction of P, that is negative charge to positive charge. This is the direction of E. So theta means it is the angle between these two. So therefore, this angle being a 60 degree, remaining angle will become 30 degree. So it is PE sin 30. So you substitute for this PE and sin 30, thereby you will get this tau. So 2 into 10 to the power of minus 8, 5 into 10 to the power of minus 5, sin 30 is 1 by 2. Therefore this tau it comes to be 5 into 10 to the power of minus 13 Newton meter. That is the answer. So as far as the board examination is concerned, in this first chapter, that is electric charges and fields, in case if any problem is given, obviously it must be one of these types. Therefore you practice these type of problems thoroughly, thereby you can confidently answer the questions in the examination. And in the next class I will take up the next chapter, that is electric potential and capacitors.